Hello, Mr. Claxton's Algebra 2 students. We're looking at parent functions and transformations. This video is to help you identify and use these parent functions and then describe the transformations. That would be translations and dilations or shifts and dilations of these functions. So looking at information that you need. So here is a list of information you need. If you want to write it down, that would be great. If you want to study it, if you need me to print it out so you can put it on your bathroom mirror, then that would be great too. This is information you need to know. You need to know what the families of graphs are. So we have constants, and that would be horizontal lines. I'm looking at horizontal lines over here, y equals 2, also denoted f of x equals 2, or vertical lines. That means that x equals 3 for every point on that line, and I've just sketched that really quick over here. I did forget to mark my y-axis. We always need to mark our axes. Outline, label, and scale. Just give me a number there. So outline, label, scale, all your axes. Linear graphs, now those are the ones we express as y equals mx plus b or f of x equals mx plus b. And then we have point slope form here as well. The parent function for that would be f of x equals x. So f of x equals x. Absolute value functions, f of x equals the absolute value of x. And then we've got quadratic functions, f of x equals x squared. So all of these are the parent functions, stuff that you should be quasi familiar with, definitely more familiar with after this lesson. Transformations. So we got transformations in general are just the movements. Those are the movements. You can have a horizontal shift or a vertical shift. Those would be called translations. So the horizontal shift happens when we affect the x value. If you think about an xy axis or an xy plane, I'm going to focus in on the x here. X, the x-axis is left and right. So if we affect that x value will shift it left or right. So horizontal shift will move it left or right. If we add a value with x, if we add that value with x, then it's going to move it left. And I know that's counterintuitive. If we subtract it, then it's going to move it right. So looking here, we have g of x, the parent function for absolute value, equals the absolute value of x. And then we have function z. Well, function z would be moved 3 units to the left. 3 units, to the right. That was wrong. 3 units to the right. Even it gets confusing sometimes whenever we look at that minus. So it's 3 units to the right. I asked myself this question. What do we need to put in this value right here? What would need to go here to make what's inside the absolute value symbols to make that 0? What value would that need to be? It would need to be 3. So looking at this, if I were going to select orange here, my vertex would go from 0, 0, and it's going to go right 3. So I always recommend just ask yourself that question. What do we need to do? Where do we need to move it? And, we should outline, label, scale here if I'm going to do things the right way. I've labeled my axes. I've got some scale there. This is a very rudimentary sketch of a graph, all right? Very rudimentary sketch of a graph, not the greatest sketch. But you can kind of see, and we do need points. In checking some of your graphs, I'm noticing that you're not really putting points on there. I would like to have at least 1 point in either direction. So we have the vertex, and let's say I enter 0 here. At 0, we'd have 0 minus 3. The absolute value of negative 3 is 3. So this would be a point. I could plug a 1 in. 1 minus 3 is negative 2. The absolute value of negative 2 is 2. So I have a point on each side. So I've satisfied that, my requirement. We have 2 rays here that make a V, right? 2 rays that make a V. This is a sketch of the graph. I didn't use symmetrical points there. only because my x-axis, I would have needed to extend that. But you can see that sketch, and that is essentially function g moved 3 units to the right. Okay, looking at f of x equals x squared, we have a quadratic function. X plus 5, what value would I need to enter in here for this x to make what's inside this quantity that's being squared, to make that 0? Well, I need a negative 5. So that means that this graph would be shifted 5 units left. So function m would be 5 units to the left. 5 units to the left. So it's horizontal shift. If you just say 5 units to the left, I'm just going to put 5 units left. And that is a horizontal shift. I know that's a horizontal shift because left would be horizontal. Okay, now we got the vertical shift. In the vertical shift, notice how we're adding numbers to the outside of the function. So we're adding it to the actual function. The function here is f of x, and we're adding k or subtracting k to that. Now that's going to behave more traditionally. For example, we take f of x equals x squared, and then f of x equals x squared plus 3. I should change this function to a different function. So if I added 3 to f of x, then it would move it up 3. So this would be up 3. Up 3 units. So this is a little more traditional here. You don't have to ask yourself any questions about what would make value 0. So again, we want to go back and just review. If I affect the x value, and that will shift it left or right. Notice how I needed parentheses to do that. They would be inside of absolute value symbols for absolute value functions. Now, vertical stretch and vertical compression. What we're doing there, a stretch is going to make it more narrow. It's going to make the function more narrow. A compression is going to make it wider. So let's go ahead and we can look at some examples. In addition to that, we have reflections. And notice when we make the function negative, we multiply essentially the entire function by -1. That's going to reflect the graph about the x-axis. So that would be like a vertical flip, right? Because the x-axis is here, and so it would flip it over that. If I'm affecting just the x values, just what's grouped with the x, that is going to be a flip of the y-axis. Now, here's the thing about that. For v-shaped and u-shaped, for absolute value functions and quadratic functions, a flip about the y-axis is the same thing because it's symmetrical. So that would be the y-axis, and if I flipped it about, that's a terrible y-axis. If I flipped about that, it's going to look the same. All right. So I've covered reflections, we've covered dilations. I like to say dilate. I'm just going to go ahead and skip ahead here to a few examples. So notice here, what value would make that x, or would make this quantity, this entire quantity right here, what value would make the quantity inside the absolute value 0, -3, right? So that'd be a horizontal shift of 3 units to the left. Okay, to the left, to the left. 2b here, see how we're subtracting 4 from the x squared? That's a vertical shift of 4 units down. All right. And then we've got some reflections here. Notice that they do reflect an x, or a linear function here. I left linear functions out because I believe you to be familiar with linear functions. So looking at, see how the negative's on the outside of the absolute value, and that's going to flip it. It's going to open down. It's going to open down. So it's going to be an upside down V. Some might call that an A, but that's going to be the general shape. We're going to get to dilations, I promise. So here's a dilation here. In the dilation, what do we have? Well, this right here would be a vertical stretch, and it's going to make the function more narrow. So if I would have a function, a parent function, right, then this function is just going to be more narrow than that. So if I had a function, let's say f of x equals x squared, and it looks like, if it looks like this, and these are just sketches, I know I didn't scale here, I'm going to save you the time. If I had a function, well, this would be a vertical stretch of 2. It's just going to be more narrow. And I think we've went over that before. We've discussed that by using, you know, Desmos or your TI-80 through your 84 plus. So it's going to be more narrow. Here, we've got a V-shaped function that's going to be wider. So if I had my original function, let's call that the parent function, f of x equals x. And then what the other function would look like is it's going to be stretched out. Now, technically, your book would call this a horizontal. That would be a horizontal stretch. That's the same thing as a vertical compression. It's going to get wider. All right, looking at those, I hope this was helpful to you. And I hope that you're able to identify the key parts of the transformations of graphs.